Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we are going to start our third lecture about this course, which is microprocessor systems and interfacing. So let's see what we are going to study in today's lecture. Okay, very first thing that we are going to see in this lecture is working register, and working register is also known as WREG register, as one can see in this diagram. This is WREG. This register is basically this is the general notation for this working register, which is WREG, and it is an 8-bit register. That means it is going to store how many bits? 8-bit, and one can see in this diagram as well that D0, D1, D2, D3, and it goes up to D7. So in total these are how many bits? 8-bit. Furthermore, working register also dictates bit size of microcontroller itself, right? So for example, PIC18F452 is an 8-bit microcontroller. That is why its working register is also 8-bit register, right? It is a temporary storage register. Temporary storage means it is used for temporary storage purpose like random access memory. That means one can store any kind of information during the execution of program. So this means it is very useful for programmer itself. For example, in any kind of application, programmer want to add some direct information inside microcontroller through the programming device, so one can use this working register. For example, we have 8-bit information. Let's say we have 1000, which is 4-bit now, and let's say the next information is 0101, right? So in binary these are how many bits? 8 bits. And if I'm going to convert it in hexadecimal, which is more obvious and easy understanding, easy for students understanding or program understanding, so it becomes 8, and the next number is basically 5 in hexadecimal. I hope everybody understand the hexadecimal and binary conversion. So this is 8-bit information, and it can easily store inside this working register, right? And it is mostly used register because programmer can frequently use this register as an interface between programmer itself and the microcontroller itself. And we're gonna see these things in detail in coming lectures as well, in coming examples as well. Okay, this is important point. It is also known as accumulator for PIC18F452 because most of the arithmetic and logical operation performed in PIC18F452 is done using this working register. So working register is also known as accumulator for PIC18F452. Okay, in this slide we are going to see a very first command, which is known as MOVLW, or in simple words it is called move literal to working, right? So move is basically for English word which is known as move, means to transfer something from one place to another place. And what we are going to transfer? A literal value. That means any number, for example, could be any 8-bit information, right, that we want to transfer. So we can simply write simple 8-bit value that we're gonna see. For example, in last example or last slide we saw we wanted to transfer 85 hex, which is a 8-bit value. So and we wanted to transfer inside working register. So the next thing that is our literal value, right? This is called what? Literal value. And the next thing, that value we want to transfer in what? WREG register. WREG register. So that means we gonna write move literal value, this value, inside this working register. So we're gonna use this command, which is move literal to working. And the syntax of this is just mnemonic of this instruction. Mnemonic means the keyword that we gonna write in assembly language programming, right? So keyword is move literal to working, that is MOVLW, right? And what is the format, how are we gonna write it? So that means move literal to working and then K. Okay, K is that literal number that I was talking about. For example, in last slide example, it was 85, so value of K here is 85 hacks, right? And the meaning is quite simple. We are moving a literal value or a literal number, which is K, into the working register. So for example, if one want to transfer 85 hacks inside this working register, or one want to move it into working register, so one has to write what? MOVLW, right? So that gonna be our mnemonic, and then we gonna write K. K is what? 85 hacks. 85 hacks. So that means this is the command that one is going to write about if one is interested to transfer 85 hacks inside this working register. So one is going to use this command. I hope this command is clear, and furthermore we're gonna practice it in our lab classes. Okay, the next command that we're gonna see in this lecture is which is add literal to working. And what is add literal to working? As its name suggests, it is going to add literal value, which can be K or any number inside this working register. Here one can write it. So what it is going to do, it is going to add a literal number, a direct number, or an immediate number inside this working register, and that will be our syntax, which is almost similar what we learned about move literal to working. So here we're gonna write add literal to working K. K is the number that we're gonna add inside that working register. So for example, in last slide we wrote move literal to working. Okay, in last slide what did we wrote? Move move literal to working, and what did we write? 85 hacks, right? So our working register after the use of this command has become what? Working register would be what? Working register value would be 85 hacks, right? So now I'm going to use this command, which is add literal to working. So let's say I want to add 20 hacks inside this working register. So what I'm gonna do, I have to write add literal to working 20 hacks, right? So I'm gonna write add, this is add literal to working, that is our mnemonic part or the keyword, and then we're gonna write 20 hacks, which means 20 must be added inside this working register. So that means 85 will be added with what? 20, and it will become, if you're gonna add it, it will become A5 hacks. I hope at this stage when you are taking this course you know hexadecimal addition. So if you're gonna add 85 hacks into 20 hacks, it will become what? A5 hacks. So next updated value of working register would be A5 hacks after the execution of this instruction. And we're gonna see multiple example in lab classes as well when we're gonna perform these instructions, gonna execute these instructions in MPLAB environment. Okay, in this slide we are going to see the diagram of add literal to working, or a diagram which explains how add literal to working command works in PIC18F. So here we see multiple elements. For example, we see ALU, which is arithmetic and logical unit, and this unit is responsible for any kind of arithmetic and logical operation inside this microprocessor or microcontroller. And what we were doing basically add literal value into W, and the value was K. So for example, K is our literal value, and that is going to be added into working register. So working register has certain value. What is going to happen? It will be added with this K value, and then this result will get stored again inside working register. So that is supposed to happen inside this working in this inside this execution of this instruction, right? So when this instruction going to execute, what is going to happen? W, which is working register, is going to add with literal value, and the result will store again inside working register. So this is our working register value, right? One can see here it is going inside this working arithmetic and logical unit, and this is our literal value, which is k here, and it's also going inside this arithmetic and logical unit, and then this arithmetic and logical unit performs addition operation, and then we will have some 8-bit result, and it is going to loop back inside this working register. So that is happening in this diagram. Okay, there is something which is extra here, and it is about status register. So we're gonna cover this topic in detail in coming lectures, but at this stage I can just say you, or I can just tell you that the status register is a register which is affected by every operation which is performed inside this ALU. So we can see that result is going to the working register. So this result is going to working register, but there is some effect which is going to this status register, and then further some effect can actually affect the result itself as well. So this is very key important register which is called status register, and we're gonna see in details. And there are certain inputs which we are observing here, and we will be clarifying their definitions while we're gonna explain this status register. Okay, next thing that we're gonna see in this lecture is PIC file register. PIC file register is also known as RAM, or random access memory, of PIC microcontroller itself. So whenever we learn about, whenever we hear a name which is called file register, so we must understand this is called what? RAM, or simple data RAM, right? So file register, data RAM, or RAM itself is a same thing, or same name for three different names for a same thing, right? So data RAM is internal register like WREG. As we learned, WREG is internal register. Similarly, internal registers, like internal register, we have some other register which we call data RAM, or which is available for user to write some certain data inside for the ease of programming, or for programming itself. So that RAM is known as data RAM, and that is also known as file register. So it is not used for program storage. We have already covered that there are two kinds of memory. One is called program memory, right? Another is called data memory. So if you remember, what did we hear about program memory? We heard that program memory is used for code storage purpose, and data memory, or the random access memory, or the file register, is used for user data, or for programmers data, right? So read write by CPU, that means one can easily read or write this data RAM by CPU, or internal microprocessor of this microcontroller, right? It's a scratch pad or data pad. It is very wonderful or very unique approach to define this file register. You know that, like this diagram, this slide, I'm gonna write so many things, I will explain you, and once I do not need it, I have to erase it, right? This is called scratch pad or read write pad, right? So this slide is right now a data pad or scratch pad for me, because I'm explaining so many things and I'm writing those things here, and whenever I do not need it, I can just delete it, right? So what I have to do, I have to select just razor and have to delete it. So this is the function of RAM itself. Whenever microprocessor or CPU of microcontroller, it needs something, it calls those data inside this data RAM, and then once it is not needed, it can be cleaned or deleted, right? So that is why it is known as scratch pad or data pad. Okay, then we come to the point, what is the size of PIC file register itself. So file register size ranges from 32 bytes to several thousand bytes. So there are number of microcontrollers available in PIC18F family. So their RAM size varies from one chip to another chip. So minimum you can find 32 bytes, and then it ranges up to several thousand. What is the size of PIC18F452 file register? Then okay, this is the same point that I explained. Size also varies within one family. For example, 4520 have different size of file register, 452 has different size of file register, 4548 gonna have different size of file register. So but PIC18F 452 that we are going to study in this course is having 4 kilobyte of file register. So remember, 4 kilobyte is what is size of file register. It is also size of data RAM, or it is also considered as RAM only, right? So you should be careful, because you know that you are going to use this microcontroller to program your application. So this microcontroller has only 4 kilobyte of RAM available for programmer itself, right? So this is very huge amount of RAM which is available for PIC18F 452. Okay, here we come to another important and interesting fact about file register that we're gonna see in further detail as well. So file register is divided into two different portions. One is called SFR. What is SFR? SFR is known as Special Function Register. That means this portion of file register is used for special dedicated functions, and those locations can only use for those specific locations or for those specific functions only, and user cannot use this for another function. So then we come to another kind of file register, or another portion of file register, which is called GPR. GPR is general purpose RAM or general purpose register, right? So GPR is part of memory or part of data RAM or part of file register itself, in which one can use for any kind of purpose. It is not dedicated, and user can use it very freely, right? So I hope you have understand the concept between the difference between the GPR and SFR, and furthermore we are going to clarify these concepts as well. Okay, let's talk about special function registers in detail. So what are special function register? As I told you, these are dedicated for special functions, right? So if you want to perform those specific functions, then you need to use those specific file register, right? So file register has a dedicated portion available for those functions, and whenever you need those functions, you're gonna use these special functions or special locations of file register itself, right? So that is why these are also known as special functions register, right? For example, ALU status, there must be certain file locations which provide you about status of ALU. So whenever you need to check those statuses, you need to go to those specific locations of file register, and you can find those status. Timers, you know that timers are very important. Circuitry, serial communication, IO ports, and ADC. So all these specific functions which make PIC18F 452 so special, and these are so special functions, right? So there must be some specific portion of RAM or specific portion of file register itself which are dedicated for these specific tasks, right? So timers have its own SFRs, means special function register. Serial communication has its own SFRs, and these portions are available, or these locations are available within the range of special function register of file register. Okay, their function is fixed and can't be modified. As I explained you, their function is fixed. These location you cannot modify it, though it is called data RAM, which must be read, write, or scratch pad by user itself, but you can't modify it. You can use it, you can put certain data, but that certain data will be used for certain functions, right? Means you can delete the information inside this register, but if you're going to write something, that will be used for certain specific function, and those functions can never be changed. That is why these functions are fixed. I mean, their functions are fixed and they cannot be modified, right? Okay, PIC18F SFRs are 8-bit register. As I told you, PIC18F family is almost all of them are all of them are 8-bit registers or 8-bit microcontrollers. So all of the registers which are found inside these microcontrollers are also 8-bit. So SFR, every SFR register is composition of how many bits? 8 bits. So if SFR have 5 different registers, so you will have 5 registers, and each of them can carry about 8 bits, right? Okay, their number varies from chip to chip. As I told you, for example, if we have 5 SFR, so 5 SFR and each of them have 8 bits, but this number 5, that means you have 5 SFRs. This number varies from chip to chip. For example, 452 have different number of SFRs. 4520 will have different number of SFRs. So these number varies from chip to chip depending upon supporting peripherals and pin. For example, some timer support for comparator purpose, for ADC purpose or IO ports, some do not support. So that is why these their number varies. I mean, these SFR numbers varies from chip to chip within a family as well. Okay, a very common rule to understand the concept of SFR: if you have more peripheral to attach, you will have more SFR. If you have less peripheral or less features available within the microcontroller, you won't have you will have less number of SFR. So I hope the concept of SFRs are clear now. Okay, here we're gonna talk about GPR, which is called General Purpose Register, or Random Access Memory, right? Or GPR, right? So General Purpose Register. So as I told you, file register has two different kind of portions. One is called SFR that we discussed in last slide, and in this slide we are talking about GPR. So GPR is basically group of RAM locations, those random access locations which are used for data storage or original scratch pad. Like this is a whiteboard and I'm gonna write so many things and then I can delete it. So similar fashion, programmer do write some logic, and if they do not find it comfortable, they can delete it or they can clear them. So this is called GPR portion of random access memory, so or file register. So GPR is that actual general purpose register, right? Again, like SFR or similarly, SFR has 8-bit registers in width, so they do have also different location. The location number may vary, but each location has 8-bit capacity. Okay, number of locations of GPR again varies from chip to chip, as we discussed in SFR. This concept is almost similar. In file register, those locations which are not used as SFR are considered as GPR. Okay, let me explain this thing. For example, you have a file register which is having around 20 different locations, right? And you know that there are 4 of them, right? Only 4 of them are what? SFR, right? This is very important point, right? So please try to understand it, right? So if you have in total 20 locations, right, or 20 registers, each of them is 8-bit wide, right? 8-bit. If these are how many locations? These are 20 locations. So every location or every register is basically how many bit? Is 8-bit, right? 8-bit wide. But out of these 20 locations or out of these 20 portions, only 4 are dedicated for SFR. So how many will be available for GPR? Those will be what? Those will be for 16, right? So 16 locations will be available for GPR. So that is why we know that the whole file register is divided into 2 portions. One is called SFR, another will be GPR. Okay, that is something that we need to know, that GPR is usually very higher compared to SFR. That means, as I explained you, 20 locations were available, so 4 locations were dedicated for SFR, and GPRs have only 16. So that means GPR is almost higher, generally higher compared to SFR. Larger the size, more difficulty you should expect for assembly language programming. Of course, if you are using 4 kilobyte RAM, that means 4096 locations are available. That means you need to address every location, and you will have different addresses of each of those locations. So you will face more difficulty to address those locations. But if you have less number of locations, for example, in I told you in example we have 20 locations, so we will have only 20 addresses to deal with. So that is why if you gonna increase the size, larger the size, more difficulty you should expect while you are going to program the assembly language programming. That's the reason C language is preferred for large GPRs, right? So whenever you're gonna see the larger GPRs, the PIC18F family members, so C language is normally preferred to program them because C language is higher language, right, or high level language. So you can easily program it. You do not need to remember each and every location of address itself. So you need to use C language, which is high level language and easily understandable for programmer itself. So if you are using a microcontroller, which has larger number of GPRs, then you should prefer C language. This is the reason that it is also preferred. But we are going to see assembly language programming in this course, so we're gonna write every program in C language. I'm sorry, in every program in assembly language. Okay, in this slide, this picture is taken from your textbook, which is already shared in your course outline, which you can find in your portal as well. So in this picture, our textbook actually explains the same concept as I explained you. So file register, if for example PIC18F this is a microcontroller and it has how many bytes of file register? 32 bytes, right? Like 32 locations they have. So 7 are SFR, so remaining will be used for GPR. 25 will be used for GPR, and this is the common rule which is valid for everyone. We're gonna see these things in detail, so we can actually go and check our original microcontroller that we're gonna see, which is PIC18F452. So it has 1792 total. In total they have these number of bytes available. So 2256 are available for what? SFR, and 1536 are available for GPR. Okay, so we discussed so many models in the last diagram, so we're gonna discuss about actual model which we're gonna program in this course, which is 452 PIC18F452. So PIC18F452 has 4 kilo locations or 4 kilobyte memory, right? So these are basically how much? 4 kilo, right? 4 kilobytes, so or 4 kilo location, which is 4096 in actual in decimal system. So each location can actually store how many bits? 8 bit. If you remember, in 8 bit are normally considered as what? 8 bit are considered as 1 byte of information. So with the instead of saying 8 bit, I can simply call them what? 1 byte. So that means every location can actually store a 1 byte of information. So that is why this is called 4 kilobyte RAM, right? Or 4 kilobyte of file register. Okay, since these are 4 kilobyte means how many bits will be used in, for example, we have how many locations? 4 kilo locations. So 4 kilo means 4 kilo. So I hope you know that if you're gonna convert them into number of bits, so 4 is basically what? 2 power 2, and k is basically how many? 2 power 10. So if you add them up, you need 2 power 12. So you need a 12-bit address to program them. Since we need a 12-bit, so you know that every 4-bit will make an hexadecimal number. So to cover 12-bit, how many hexadecimal symbols will be used? I mean, to cover 12 bits of address in binary, we need 3 different hexadecimal symbols. So that is why 3 symbols are used. 00 hex. So initial address will be what? 00 hex. And if we're gonna write the maximum address, that will become every hexadecimal start with 0 and maximum number can go to F. So that is why the maximum address which is available in 4 kilobyte of RAM or 4 kilobyte of file register is FFF or FFF hex, right? So address starts with this 000 hex and it goes up to FFF hex, right? So this is the maximum address that you can have in this file register, and this is the minimum address that you can have in this file register. Okay, furthermore, for the ease of programmer, this 4096, this is huge number of locations and it's very difficult to deal all of them at once or in one go. So that is why these are divided in different chunks, and those chunks are known as banks. So there are 16 banks or 16 different portions available in these 4096 locations. So these 4096 locations are further divided into 16 banks. So if you're gonna divide 4096, right, with 16, so how many what would be answer? That would be what? 256. I hope you can easily do it yourself, right? So what is this number? In total we have how many locations? 4096 locations, and those locations are divided into 16 parts. So how many parts we have? 16 parts. So that is the capacity of each part, right? That means in each bank we have 256 bytes. So that is why each bank's capacity is how many bytes? 256 bytes, or in simple words, we have 256 locations available in each bank. And if we gonna write the total capacity, we can easily calculate it by multiplying 256 with 16. So this will become again 4096 bytes. I hope this calculations and this conceptual integration should be clear to all of you now. Okay, that's it from this lecture. Today we learned two different important registers, file register and working register. I hope you have grasped the concept. If you have any query or any confusion you didn't understand, you can comment in comment section. Thank you so much for listening.